Okay, we're going to look in this today. We're going to look at exponential functions. So before we get into the functions part, just kind of a reminder. I don't want to do that. About these different parts of this. Say, you write a number in this way. This is called the base. The superscript is called the exponent. So when we refer to those things in this section, you know what we're talking about. Obviously, this is kind of basic stuff, but just want to make sure everybody's aware. Base, number, exponent. All right. A couple of special bases you'll see. There's 10. So 10's a special one. Sometimes you can find, if you want to take 10 to a power, you just say 10 to a power in a calculator. But you can also a lot of times see if you hit a second button, and then you might have a button that says log. You'll usually have 10 to the x or something. Then you can use that to raise 10 to a power. The other special base is a number called e. It's Euler's number. It's an irrational number like pi. And if you want to raise that to a power, then you can usually hit second and then a button that says ln, and it's usually its second function is e to the x. So to get that, so if I said, what is e to the third approximately for, let's say I was using this calculator. It's a little different than some other scientific calculators. So on this one, I do the exponent, then I do the e. So if I said 3 second, and then my ln button has turned to e to the x, I'd hit that. And so that's about what, 20.09, let's say, approximately. So that's the way you can calculate it. If you want to just know what its value is, you can always just raise it to the first power, 1 second ln, and there you go. That's the irrational number e to however many decimal places that is. That gives you a good approximation for it. So the first few problems are just going to ask you to do some calculation, and then they're going to get into the exponential model and exponential functions. So that's my thing. All right. So exponential function. We're just looking at the basic one. There's obviously a lot more complicated versions of this. This is the basic one. Y equals some number to the x power. Now, there's going to be two graphs of this. If the base is bigger than 1, or if the base is between 0 and 1, but they share some features there. So the graph, if the base is bigger than 1, looks like the following. It's like that. And the base is between 0 and 1. The graph looks like this. So the first one, where the base is bigger than 1, you can say this is an exponential growth model. Things are getting bigger and bigger exponentially, whereas when this base is between 0 and 1, that's an exponential decay model. Okay. So they both have a y-intercept at the same location, 0, 1. If we look at their domain, these go left and right forever. So all the way from negative infinity to positive infinity, left and right. The range, the y values, these are bigger than 0. Y is bigger than 0, so 0 and up. And then these have a horizontal asymptote at y equals 0. So there is a guideline here that this approaches but doesn't touch. And there's more complicated models for a lot of like natural systems. They would use something more like this, and this might be modeled using something like e to the x squared. You know, so that's a little bit more complicated model if you're having like infection rates or something. You know, grows and then it kind of peaks out and then comes back down. That might work for that kind of model. But we're not going to specifically talk about those models, though you might run across them. We're going to stick with the more basic setup. So let's say I want to graph y equals 3 to the x. So I would look back here and I would say, well, my base is bigger than 1, so it's this first situation. So I just draw that picture. Crosses at 1, goes like that, okay? And you might wonder, you know, where's the 3 at? Well, what this is telling you is every time you take a step to the right, you get 3 times higher. So the next spot, if I took 1 step over, would be at a height of 3. I guess it would be here. It would be height at 3. So it'd be 1, and then it'd be 3, and then it would be 9, 27, 81, and so on. Same thing if you go backwards, your 1/3 is high. So this spot right here would be at a 1/3, right? So then it would be a 9th, a 1/27th, 1 over 81, 1 over 243, so on. So the base number itself, if I just say sketch a picture, we're not plotting a lot of specific points. Really, the only point I care about is this spot. What happens to this spot? Where does it go? Other than that, I'm not really worried about it. If this is 3 to the x or 2 to the x or 5 to the x, they all have the same general shape. It just affects kind of the steepness of it. All those transformations we talked about still apply. So if I want to graph y equals 3 to the x minus 2, so notice where that is on some calculators. If you needed to type that in, you would have to put parentheses here to type that in your calculator to graph it. And what we would see is this is a move 2 units to the right. So I'd take this original picture and I'd move the picture 2 units to the right. I draw that dot, because remember, that's the only spot I really care about what's happening to it. And I'd get that curve. Or if I said, let's graph 3 to the x minus 2. So notice the difference between these two. This time, the minus 2 is minusing the whole function, not just the x. So that type of change is to move 2 units down. So I take that original picture and I think I'm going to go 2 units down. So I start at 1, down 2, would put me at -1. But I also had a guideline at 0. Well, now my guideline is going to be at -2. Everything about the graph moves down. So now I have a picture that looks like that. If I want to graph y equals -3 to the x. So order of operations, say you do exponents, then multiply. So I would do the power, then the negative sign. So this is not -3 to the x power. This is 3 to the power of x, and then the opposite. Well, what that type of change is, when you do that, you're flipping it over. I don't know why I'm not getting my line drawn here. All right. You flip it over the x-axis. It's reflected relative to the x-axis. That's what that graph would look like. If you instead put the negative on the x, what that would do is it would flip it over the y-axis. So I'm thinking this original one flipped over the y-axis now looks like this, which makes it now an exponential decay model. Well, that makes sense because a negative exponent tells you to do the reciprocal. This is the same as a 1/3 of x. So in some textbooks, they may not even talk about what if you have a base value between 0 and 1, because that just means you can make a negative exponent and flip it sideways, reflect it relative to the y-axis. That's how you can make an exponential decay model. All right, and then I want to do one more example here. Y equals, let's say, 2 times 3 to the x. Well, again, order of operations, you do exponents before multiply. This is not 6 to the x. This is 3 to the x times 2. Well, what that does to the graph is it's a vertical stretch by doubling the height. So if you think about the original one has a height of 1, this height is doubled. So now it has twice the height, but it's still, if you double 0, it's still 0. So it didn't move up, it just got stretched vertically. And so that's what that graph would look like. So all those transformations we talked about before, they still apply in this case. All right, and then I'll talk about next how to do some compounded interest models on the next video.